Few announcements. You must have received your marks for the proposal and the midsem demo. You will also receive an email saying why the marks were deducted. We'll be giving out the reason. So you don't need to send immediately emails to all the TAs asking for what was the reason. You will get an email. Just wait for it. I think you will get it today. Second thing is, this is midsem demo. This is not the final one. And the final demo is there. And right now, all the group members, those who are doing group projects, should have received the same marks, right? It's just the placeholder. At the end of the report, we will see overall in the project how much efforts you put. And we will ask you the equal amount of work, right? You share the same marks with your fellow also, the peer who has not done anything, right? So it's your call. So we will talk to you and you have to give us the answer, and it's your call if you are okay with sharing the marks, and it's relative grading finally, right? It's your call. Second thing, yeah, that one is there. Okay, now this is 1 week and you have 1 week more before we, right? So next week, so this week probably end, I will post an assignment on the topics that I have covered so far in wireless, right? And so that you get an idea again as to what would be the type of questions you'll see in the final exam, right? And I will post the answers, so you will get also the answers. So be prepared for that. Your demos will be, I think, after your exams, but again, that timetable is being decided right now, when you will have the end-sem exams and when the demos and everything. As soon as I know it, I will let you know. Okay, do you have questions about grading for the demo and so on? No questions? Yes. It's an error. So that you send me email. Yeah, send me an email. I will. There is some typo there somewhere. It's the same proposal. What is this? Okay. So I will give you a template also for the report. The final demo will be demo. You have to submit the code. Usually I ask you to upload it to a Dropbox folder and then share me the link, because sometimes the code is large. You have to also give the compile code and so, right? Source code and compile code. And that you may not be able to upload on Backpack because of the limit. So I will ask you to upload it at a Dropbox folder, make it publicly visible or at least visible with my ID, and then put that link in your report and you upload the report on Backpack. Right? So report has other things, and one of the things is linked to that Dropbox folder where you have uploaded the code. Yes.
What time will be getting comments regarding
Today, I asked Nikita. I think she should be able to do it today. Yeah, so we discussed it, and the comments should reflect that. They were also told, instructed that you should look out for this. Right, so, but one thing to realize, this is, right, demo is not something which is mathematical, right? You can't say this is 2 plus 2 and my answer is correct, right? So that's why there were 2 to 3 or 4 people judging it, and they had unanimously decided this is this level and that level, right? So you will have to respect that thing also. It's not that we cannot absolutely say this is 10 or this is not 10. Right? So that there is some relativeness and all in all that. Okay, and then I said last time we'll upon some of you. Now we have the marks, right? So I will send out an email. I will call upon some of the groups to show me the demo, right? And that those about it. Right, now let's back to the wireless. So we will try to finish given the timeline, right? Probably next week I'm not going to start any new topic. I will do some revision and some question answer so that you don't, and then you spend time on the assignment rather than I start something new. So last time we discussed routing. It was mostly introduction and refreshing of concepts of routing. And then we discussed what is the routing table look like, how you can write one, and then we discussed different types of routing protocols. So to be precise, this is the categorization. We have some which are proactive and some which are reactive. What's the difference between a proactive routing and a reactive routing? Anybody? Who's?
Acts when something changes.
Right.
Whereas the proactive is always waiting that this change.
Right.
Even if this change, we are ready with this.
Yes. So proactive always is engaged into looking at the routing table and it keeps on building. Reactive is something not only when something changes, but when somebody demands an output, then only you go ahead and do something. And that's when it's reactive. Proactive is even if there is no demand right now from the transport layer that I need to send, in fact, will build up a routing table and be ready with it. So that's the difference. And then you can do a combination of these. It becomes hybrid. Example of proactive routing is OLSR, which we'll see today and maybe next class. Reactive is AODV. I would have loved to complete AODV also in detail, but these two are involved topics, so I don't want to rush it. Maybe those who take Sanjeev's course will learn more about AODV. That I think I can leave it out if we don't get time. So OLSR is linked state routing. It's based on the standard link state protocol, but we are going to optimize something on top of that. So it's an optimized version for us. Anybody remembers from the last class what is the optimization we thought of? Then on top of the standard routing protocols, if we want to go to mobile, what kind of optimizations you can do? Or what is an unoptimized routing protocol? Let's see, answer the simple question. Yes, recalculate. Every time there is any change in that whole topology anywhere in the graph, right, you execute the routing protocol and that's your routing. Right? So that's an unoptimized, simple, trivial way of doing routing. Today I will show you how we can optimize it. So we don't do that much of work. So categorization wise, this is a table driven proactive routing table. So you get a routing table and it is a proactive. That means it initiates itself even if there is no need. And so route is immediately available whenever you need it. You don't have to wait for the route to establish. It's based on the link state protocol. It's will flood neighbor information just like you do it in the link state protocol. There is flooding of packets which will go across the network, everybody gets it and everybody knows it. That's what the links. So let's see, come back to this one. This is a little higher. Since the advantage of periodically sending anything is if anything is lost, a packet is lost, right? You don't have to recover that packet immediately. You send it again and again and again, and you will receive it eventually. So that's how it is reliable, right? Because it keeps on flying. It does not need any in-order delivery. This is an important point. You will not appreciate in this course. Maybe in the fourth year you take some course, you will understand this. But the good part of this protocol is I send you a message and I send you another message which comes before the first one. That will not poison our routing table. That will not create any bad effect on the routing. Right? So my messages can get out of order. It can come at any point in time and still the routing will work. Right? It's very interesting to have this property. Right? So this one has got it. You use sequence numbers and you use hop by hop routing. Means you do not have the entire path. That's the difference. You just know where to give the packet next hop. That's it. Now let me ask you a question. This is, let's say, our network. Don't look at for now these technical things. Right? This technical jargon I will explain now. If you just look at this as a graph, and this is our topology. If every node sends information, what will every node send as an information in the link state protocol? If I execute the link state protocol, what will be the message for every node? Just the neighbors, right? So one will say my neighbors are 4 and 2. It will tell 4 and 2. 4 and 2 will tell it to everybody else that one's neighbors are 4 and 2. Okay. Can you optimize this? What will be an optimization for us? So let me not show you this. Then we start the video. 1, 2, 3, 4, 5, 6. So this is, let's say, my network looks like. So one says I'm connected to this way and this way. Everybody. 1 to 4, 1 to 2. And it goes throughout the network, this information. Question is, how can I reduce the number of messages in this network? So while this information goes here, this goes here, this goes here. What's next? This message goes here, this message goes here. What happens at 3 now? Right, so what does 3 get? It gets this message. And what is the next message we get from 2? So it will get this one as well and something else. Right? So this something else is 4 is connected to 6, 4 is connected to 3, 4 is connected to 5, and 2 is connected to 3. Right, that's it. So do you think there is any chance for us to reduce this? So 3 gets 1, 4, 1, 2, 4, 6, 4, 3, 4, 5, 1, 4, 1, 2, and 2, 3. Do you think there is a way we can optimize this? Optimization means reduction of messages. The less you talk, the better it is. What will be an optimization? Right. So you see, this is right. This is an extra piece of information. I don't need to know again and again that one is connected to 4 and one is connected to 2, and somebody else also saying me the same thing. So how would you reduce it? Everybody got the suboptimal part. And if you just use the link state, 3 will get information saying 1 is connected to 4, 1 is connected to 2, from 4 as well and 2 as well. But that now becomes, you have to mathematically say who will say what. Right? You can't just, I know that when you do this and you will reduce the message, but it should be applied to every node in the network. And locally you should start thinking whether I need to send this message or somebody else will send it. I don't need to do it. Okay? The question is, if I can use the same link state protocol, but now make every node smart and decide locally whether I need to send this again or somebody else must have sent it. Right? So I don't need to do that. If you can devise a protocol like this, then you can it becomes optimized. But now the hard question is who should send it, who should not send it, and how should I know as a node whether I should do it or not. That's the hard part. It's not easy to do that. So that's where the whole concept of OLSR. We'll see how we can mathematically do it. Okay.
The connections are bidirectional.
Yeah, it's all bidirectional.
So why one has to send 1 to 2 to 2? I'm asking that one is sending to 2. You should only send 1 4. Why one is sending 1 2 also? Because 2 is
right.
2 knows that
Okay, that point is okay. So if for the direct connection, you don't need the other node to say it, right? But you will send some information. See, there is another node here, node A here. Now that 2 is not aware of, right? Only 1 is aware. So he had the node 1 has to talk about that. You can make it better, little better, by saying that if you're directly connected, you don't announce it because the neighbor already knows it. Right? But still, my point is that this node, right, you will, so 2 will still say I'm connected to 1, and 4 will also say I'm connected to this, and this other thing also will come there, right, and it will get 2 copies of it. Or let me just say, if this is the how it is connected, right, so it will have another thing here. In this one, right, this will also be there, 1 comma 8, and you will get 2 copies of 1 comma 8.
One way of finding all the cycles in the graph. So, there's a cycle connecting 1, 4, 3, 2. There is a possibility of getting 2 messages from 1. That case, we'll be able to find out that avoid all the, if there is any cycle, then only 1 node should be allowed to advertise the connections. Neither one.
Right. So it's not the cycle, there is something else in that. There is a property that you see. Cycle will also apply. There is another property, right, which will identify. No, you don't know the topology. You know the topology by exchange of these messages. And we want to even reduce those messages itself. So you don't, right? So that is a good point. So you need to send something and find it out, right? You don't know the entire topology, and we want to reduce it. Right. Yes, something from 5. Right? So we have now, at least we know what we don't want. We don't want this, right, in the network. We don't need to get 2 copies of the same thing.
Instead of sending the paths, like if they sending that 1 and 2 are connected, what they can send is like the reachable nodes. From where can you reach? Like just send the information like I know where is 1, I know where is 2. So just instead of sending the information like 1 and 2 are connected, just send that I can connect to 1, 2. This out. Yeah.
Yes. We'll yeah. So we'll expand on that. You're saying that not just 1 hop, but 2 hops.
Yeah.
See, you will get implications like this at the two-hop layer. At the level of two nodes away from you, you will start receiving these things right, together. So you should not only look at your neighbors, but you should also have some idea about neighbors of your neighbors, so friends of your friends, like in the Facebook terminology. Right? You should know about your neighbors, and you should also know something about your neighbors' neighbors and how they are connected. If you know that, then you can tell your neighbors, don't send it. Right? The neighbors will give it somehow or get it. We'll see that. Right? But you should know about one should know about 4, 2, and 3. All the way at the two-hop level. Right? So let's see the protocol, and then we'll again come back. Okay, now I'm defining some sets, and we'll define it in terms of these nodes. Each node N in the network selects a set of neighbor nodes as multi-point relays. So in your neighborhood, you say some are relays and some are not relays. Right? So what is a relay? That we have to find out. So for example, if one says 4 is my relay and 2 is not my relay, that means 1 is designating node 4 to talk about itself, and it is telling 2 to do not talk about me to your neighbors. If 1 can do that, then 4 will act as a relay or as a designated node to talk about 1 and 4 connectivity, right? And 3 will only get 1 piece of information. These are called the relays. Is this concept clear? The concept of relay. So I designate somebody, right? It's like my brand ambassador, and then I say, okay, go and announce for me, right? Only he will announce, nobody else will announce. And if only he announces, right, we'll make sure that you don't get multiple copies. So how do you select this now? If I want to select some, see, it has to be from your one-hop neighbor, right? So if I have 10 neighbors, I have to select, let's say, subset of it, so that everybody in the two-hop gets a copy. See, if I select very few relays, what will happen? If I just designate very few relays, what is the issue with that? There is a problem with that. May not receive it. Have a path. So if I just select very few nodes, it might happen that my two-hop neighbors, all of them may not get it, and because of the lack of connectivity. Right. If they are forwarding again and again, right? But if they are not forwarding again and again, right, you just forward once. In that case, it's saying that there could be some node which may not get that. Right? That's the one side. What is the other side? If I every network and you get multiple, somewhere in between, right? So that way the two-hop gets it, but nobody gets a second copy. So how would you do that? How would you select only those nodes so that everybody in the two-hop gets my message, but nobody in the two-hop gets it more than one? Very good, right? So if I don't select 4, let's say if I select 2, what happens? If I select 2, so if 1 selects 2 as is designated or relay, what will happen?
6 and 5.
Right. So, but this 6 and 5 2-hop away from 1. Right. So which are the 2-hop nodes? Right. So this is 2-hop node. This is a 2-hop node. This is a 2-hop node. Right. So these are 2 hops away from 1. So all of these should get it. Right. So if I select now 2, 3 will get it. 5 will not get it. 6 will not. Right. So if I select 2, I have to select 4 as well to cover up the thing. Right. But then it becomes, it might be multiple copies, right? So, but if I select 4, 3, 5, 6 get it, right? And I don't have to select. So this can become my relay, and I don't select 2. So if you are to select or design a protocol now, how would you do it? What is the information? See, one has to decide. One as in node ID, one should decide whether to select 4 or 2. So what is the, now mathematically, what is the protocol? You have to say it in terms of messages, right? And there should not be any ambiguity in these messages. How can one decide that I should select 4 but not 2? High degree is right, but not just high degree, right? Because high degree doesn't cover the entire 2 hop. Right. So you should first know what are your 2 hop nodes, neighbors. Right? As at 1, node ID 1, I should know that from 2 hops away from me, that is 6, 3, and 5. These are the 3 nodes. Right? So all these 3 nodes should get this back. Right? So you start from there. And then what you do is you know your 1 hop neighbors. And then what is the one piece of information that's remaining? I know my 1 hop neighbor, I know my 2 hop neighbor, but I should know something more. How many? Yes. How this 1 hop is connected to 2 hop? I should know that one also. Right? So if I know 1 hop neighbors, I know how they are connected, then I can derive what are my 2 hop neighbors, right? So I should know 1 hop and their connectivity. Given these 2 information, I can find out who are 2 hop neighbors, and then what is the next step in the protocol. So brute force protocol now. Let's do it in a brute force manner. Yes. Right. Right. So if you know the complexity, right, order big O notation, right, we can just go through all of these 1 hop neighbors and select one at a time. And let's say you have n nodes, n 1 hop neighbors, 0 to n minus 1. Right? You select one and see how many 2 hops you can reach. Right? And then you can try all permutations and combinations possible. How many possible permutations? How many permutations do you have to try out? So if we have, these are your 1 hop. So if I have n and 1 hop neighbors, then what is the brute force method of finding my optimal relay points?
Because each of the 1 hop neighbor will take.
Yes. So so you're saying n into something. Right. You're saying n square y.
Then one can have other possibilities also, other inputs. So then typically second lowest will that, and the first one goes 0 to n minus 1. So n square.
N square. Anybody thinks it is 2 raised to power n? Why?
If you choose one out of from the n, one what do you
Yeah. See, this will give me, what I have is n possibilities, right? And you can think as it's a bit as a relay or not. Yes or no. So that means I get 2 options at every point, right? 1 or 0. And then I can try all possible combinations and I have 2 raised to n. Right? I can have all of them as relays, so all yes, and then I have all possibilities. And nobody is relay, that's all 0. Right? And in between everything. Right? So I try everything and then I say this is optimal. Because this is giving me the least number of yes. Right? So what you want to minimize is number of y's. Yes. At your 1 hop. Okay, so in all this all the way to all nodes, you just find out anything that does not give you 2 hop connectivity, you eliminate that. You reject it. Right? Whichever gives you 2 hop connectivity, you keep it aside. And then all these assignments you have to be kept aside. You just select one which has got the minimum number of yes. Right? And that way you have an optimal. Anything which, see, any optimality problem, if you want to do it by brute force, it will come out to be like this. Right? Because you're basically trying out everything. Right? So trying out everything is this one. Okay, so that's, you have come up with an algorithm that is giving you the best possible relays. Now we'll put it in terms of math so that I can write it and explain it to somebody else as an algorithm. And this is what is a distributed algorithm. The one thing that I will explain today is a one distributed algorithm, right? And we have an entire course also which talks about more distributed algorithm. Right? This is something which is not sequential. Right? It's distributed. And the way it works out is, I define something called MPR, multi-point data set for every node, right? And this is the node which I am designated to send my control packets. And it is selected, MPR of n is selected such that all 2 hop nodes of n, 2 hop neighbors of n are covered by my 1 hop neighbors of MPR. Right? So this is now I am giving a mathematical notation that I have explained to you in intuitive language, simple English. Right? Is this definition okay? Have you understood the definition map between what I said and what is this is saying? Take a moment, just read it and see whether you can accept it or internalize this. Okay. So what is MPR? One. MPR of that's what we, right? And now if you want to see it is doing MPR of 4. You can think whether this is right or wrong. What is MPR of 4? Look at 2 hop neighbors of 4, which is 1, 2, 3, 5, 6, and actually 7, entire network. Right? So at 2 hops away from 4, you have the entire network. And you should select from your 1 hop nodes, neighbors, so that everybody in the 2 hop is covered. So you see whether 3 and 6 is sufficient to cover everybody. So 3, if you select 3, then 3 will cover 2, 5, right? And if you select 6, it will cover 5 and 7. This is valid or not 2 hop, and this is 1 hop. So I don't need to worry about covering this.
Will 5 be considered 1 hop or 2?
It's 1 hop, right? So you don't need to really cover it. Right? 5 is 1 hop. Now, is this the only MPR of 4, or is there any other which is MPR of 4, which is equally optimal? No. If add is not optimal, right? Optimal means what? Right? This is containing 2 nodes. A better one will give you 1. See, I don't need to go to 3 because if I know already with 2 nodes, right? I have an optimal. So can I select just 1 node, which will cover my 2 hop for node 4? Because I'm saying, can it be just 1 node? No? So you can't, can I just select 5? MPR of 4 is 5. What happens then? You can't reach 2. Right? This is 2 hops. Right? So that's not possible. Okay? 3 and 4. So can I select 1 and 5? Right, so if I select 1 and 5, then 7 is not covered. So let's see, I have to select 6. So I have to select 6. Right, because that's the only way to reach 7. Right, so I select 6. Now out of 1, 3, and 5, you can select 1. Then 2 is covered. 4, this is 1, how to see 1. Right, so the other one is 1 and 6. Right, so I can go with 3, 6 or 1, 6. Right? So there are two optimal points which I can select and I can still cover. So it's not unique. You can have multiple other choices. Questions? So with that, what happens is 4 says to 3 and 6 that you will represent me in the network. If I give you a message, you should send it to all your companies, right? And it tells 1 and 5 also that you don't have to take this. You will receive a message from me when I do a broadcast, but you don't give it to anybody else. So you have to do that one also, right? You have to tell 1 and 5. You are not my leaders, and to 3 and 6, you are my leaders.
They can't forward it.
Right. So we'll define it, but they will not be asked to forward anything. Yes. See, optimality is hard, and this is not the topic of this lecture. Right? I'm not going to go. I gave you a brute force method of optimality. There are better ways of coming up with optimality. Right? Those algorithms are complex, so let's not go into there. Yeah.
For setting NPR, you should know the complete graph or only the two hops.
Right. So do you know? You need to know the complete graph, or 1 hop, or 2 hops, or 3 hops. Only 1 and 2 hops, right? Now, once I put it as a maths, right? You can see I never talk about the whole network. I talk about everything in terms of 1 hop and 2 hops. So you should know only that much.
But sir, if the network was such that there was a 3 of neighbor of 4 also there, connected with 1. 1 connected to some number n and n connected to some number x. From 4 to reach x, the 1 should be one of the relays for 4. So for that, I should know that there is a 3 of neighbor of 4 also there. So I should be knowing the complete graph, isn't it?
The question is, you need to know the complete graph. Because there could be a long connectivity coming back. Right, why? Okay, so let me, you can answer it at multiple point of view. One thing is, right, to reach 3 or 4 or 5 or n hops, right, you should first tell who will forward it. They're not going to know by itself, right? Somebody at the 2 hops should forward it, right? So you have to first tell at 1 hop and who should forward, and then the 2 hops will get it, and then the n hops will.
Exactly. To select this 2 hops, I should know the 3 hop neighbors of mine also. So that every 3 hop neighbor of mine is covered.
No. We'll come back. So I have not talked about what happens at 3 hops, right? I have not so far talked about what happens in 3 hops, right? My question was, how do I cover my 2 hops using this knowledge, right? And that is the only question I answer. Right now I don't say what happens at 3 hops and what happens at multiple hops. Okay? So I should tell at 1 hop level who should send, who should not send. So that my 2 hops gets covered. That was the question, and I think we solved that question. Okay, now let me complicate it a little bit, right? And then we will see the whole protocol, right? So, like we discussed what is MPR of a node in terms of MPR in bracket N, right? I will define another set which is MS. And this is the complement of MPR. What is the complement of MPR? It's not that one. It's or not. I shouldn't say a complement of it. Right? It's not the negative of it. Right? So let me define it and then we'll see. So MS of a node is the. So if I see MS of 3, it is all the nodes for which 3 is acting as a relay. Initially, when I said NPR of n means n is myself and who will be my relay. And now I am defining MS of n, which means as for which nodes I am acting as a relay for representation. So, in our definition, MS of 3 will contain 4 because I am acting as a relay for 4. And MS of 6 will contain 4 because because 6 is acting as a relay for 4. See, this is not a new piece of information. If I'm given NPR of every node, I can derive MS of every node. It's just another order of it, right? It's not, there is no difference. You just need to know NPR of, and this is, you can derive as a second order information using the first steps. Yeah, it will contain more nodes. If somebody else has also selected 3 as the relay, it will contain that thing also. So this is MS of 3. What is the piece information that MS gave at node 3? If I tell this to node 3, what happens? What is the information 3 knows now? Yes. No one at a time. Yes. Right, so MS of 3 is all these X, Y, Z nodes. That means if I receive anything from X, I should forward it. If I receive anything from Y, I should forward it, and same thing for Z, and not for anybody else. Right, so I can tell node 3, this is your MS6. Right, and that gives us enough information or sufficient information to forward packets on top. Right, so that's MS of a node. So now let's define it. It's the set of nodes that chose or that choose node N in their multi-point DSA. Right? So this is what it is. So with this, so every node should know its NPR set, and every node should know, right, its MS. So for whom it is going to form. Okay, now let's combine this, and now let's start the protocol. Right? Yes. Three and 6, yes. Right. So you select one of these options. Either, right. So 4 selects beforehand, either it will go with this and this. Just like in the routing, you have 2 paths of equal distance. Right? You don't use both of them. You use one of them. And both of them, by the way, are equally good. But you use one. So in this case also, even though there are 2 optimal sets, you will use one. And you will stick to that. Right? You don't have duplication now. Okay, now let's finish the protocol and then we'll see how it is going to help us out finally. So each node now uses hello message to determine its NPR set. So everybody is saying hello, I'm there. Right, my ID is this and hello. Just like you go to a conference and you say hello to everybody, these nodes will start saying hello to everyone in the one hop, right? And say my ID is this, my name is this. Right? And we periodically broadcast this message to only one hop neighbors, and we have all bidirectional links. That means if I hear from you, you should hear from me. So with this, after all lots of rounds of hello messages, you will know what will you do. Only one hop, not everybody. All one hop neighbors. And you should just know who are your neighbors. Okay? Right? And these messages are not forwarded. So I'm not flooding the network. That's where I cut it down. I don't tell, okay, you say hello and then you convey my hello to somebody else. Right? There is no conveying. Just say hello to once, only one hop, and that's it. And so hello of this will give to 1, 3, and 5, and 6, and they will come to know they are directly connected over one hop to node 4. Now using this neighborhood set, so after, because 4 will get this message from 1, 3, 5, and 6. So it says my neighbors are 1, 3, 5, and 6. Once you know who your neighbors are, and you use that list in the received hello messages, those can determine their 2 hop neighborhood. How do they determine 2 hop neighborhood? Okay. So hello message contains its own ID also and later on its neighbors also. Right? First thing you say hello is your own thing. But once you receive hello from your neighbors, you know what your neighbors are and you put that information inside your hello message. Right? So after this round of hello messages, what everybody will learn? 2 hop neighbors. Right? So first round you know your neighbors, second round of hello messages, because every hello message contains the neighbor set, right? You get that. And you have to do it few times. Because some nodes are very slow in saying hello. Right? Some nodes are very fast in saying hello. And you have to make sure that you give time to everybody. And after that, Right? You have hello messages containing 2 hop neighborhood. So 4 will now know 1, 3, 5, 6, and the 2 hop I have 2 and 7. Because 6 hello message will contain 297 in the name. Now can you find out an optimal state using this? Which is the method we'll use to find out the optimal NPR? So note 4, if you want to read this out, right? Neighbor of 1 is 2, neighbor of 3 contains 2 and 5, neighbor of 5 and so on, right? Okay. Which method will you use to find out your NPR? Optimal NPR set at node 4. We discussed the method. So node 4 knows now it's 1 hop neighbors and 2 hop neighbors. How will it come up with its NPR set? Right, this method, right? Our brute force method. Just list it out, you select each one of these, right? And you go with all possible permutations and you select optimal set. So after this, 4 will know its NPR, right? So after this, subsequent hello message also indicate neighbors that are in those NPR. So now the hello message is getting bigger and bigger. Initially, you just announce your own name, your own ID. Then you announce your neighbors. And now you will announce your NPR, saying I am designating 3 and 6 as my neighbor. Okay. Now what happens after this one? What does every node knows now after this? Can you list out the things that every node knows now in the network? All hop neighbors, 2 hop neighbors, and MS. As a node, so NPR you know because you calculate your own NPR. And you know now what is your MS, right? Who all have selected you, right? So after this message, 3 and 6 knows that 4 has designated us as a relay. I'm selected by 4. So they have a new responsibility now, which is after this point, our basic network is created in a way at 2 hop layer. Right, so you at least should have 3 rounds of this. You will need more of it, but at least you should have 3 rounds. Right? In the first round, you announce yourself. Second round, you know 2 hop. Third round, you know NPRs. And after 3 rounds of hello messages, everybody will probably know that this is the sex. Okay? Questions? So now if you see this network as designated 3 and 6, so can you find out, now do an exercise and find out NPR for every node. We have done it for 4 and we have done it for 1. Can you find out NPR for 3, 5, 6 and 7? Okay. Do an exercise, right? And find out, I want to know, so you said NPR of 4 is 3 and 6. NPR of 1 is 2 and 4. Now I want it for 2 or for 3. What is NPR of 1? Only 4. What's ampere of 2? Is it, can we do less than 3? Firstly, let's 3 is fine. We connect between 5 and 4. And then the two of tables are 4 and 4, actually just 4. No, like 5 also. 3 is fine. So let's ampere of 3. NPR will be 1 count away from me. Can't be 2. So with 4, next NPR of 5. So 6 for sure, because that's only we use 7. NPR of 4 also, because 1 is 4 only. Right, so you select 4. In 5. This one?
3, 4, 6.
You need more, NPR of 5. You need 3,
4, 6.
can you do it less? An NPR of 6. So now can you write MS? Right? This is NPR, right? Now it is MS of 1. What is MS of 1? It's empty cell. Nobody selected 1. Right? And MS of 2. Nobody selected. 3, 2, 4, and 5. 4, 1, 3, 5. And 6. Five. Nobody selected. And 6, 4, 5. See, by the way, this is not only applicable to computer networks, right? This is the standard thing Facebook also uses all the time. For what? But where would Facebook and Twitter will probably use it? Or Airtel, Vodafone, everybody. Anywhere when you see people are connected, you will use it. Why would I use? What is this special? See, who is most popular here? All these. Not most popular, but most burden. What's so special about phone? Highest connectivity, right? So if I'm an Airtel or Vodafone, right, and I want to see whom should I give the maximum, right, weightage, so that I don't lose that customer. Because phone is going to do a lot of forwarding. He's making lots of phone calls and messages. And he's connected to so many people. So they will be very nice to number 4. Right? Rest, if they leave, that's okay. It's Facebook. Right? Number 4 becomes important because if I send something to 4, he will forward it. Right? So for them also, number 4 is very important. Right? So it's not about just the computer networks, human networks, medical. From medical point of view also, this is important. Right? 4 is the one who will probably spread maximum diseases and infectious diseases. We go to 4 and 4 almost very fast. Right? So this is not only applicable to networks of computers or routers. Everywhere you will find out. Twitters, online social networks, medical, airline networks, any networks. Right? That is the kind of study they do all the time. Right? And this becomes, and you want to reduce this optimality and so on, and that's why you have complex algorithms. Right? So you came up with this, right? And now we just see the final protocol and tell every node what to do, and that's it. And now we ask a node to send a message called topology control message, TC message, which will advertise the neighbors and it will have a sequence number. So these are the relay nodes that are selected in the network. They become special and they talk about topology of the nodes. Rest everybody is quiet. Right? And if only they talk, I can still reach out the entire network. Okay? So a node generates a TC message only for the neighbors in its MS set. What does it mean? Only for the nodes in its MS set. Can you translate this to English? I know now this will get complicated, right? So think about it and translate this to English and tell me what's happening. Only for the neighbors in its MS set. So if I am the node, who is in my MS set? The nodes for which I am the relay. So what it is telling that node or to me that I should generate messages only for which I am the relay or I am the caretaker. Right? I don't worry about everybody else. Just worry about who has selected me. If I am the representative, I got elected right, in the parliament, I should just worry about who elected me. Right? And then do something about that. Right? So he does it, and then only NPR node generates TC messages. So who is supposed to generate a message? Only those nodes which are relays. Rest everybody is fine. So as a relay node, I should generate a TC message and I should generate it only for the node who selected me, not for everybody in my network. Okay? Right? And I should send it now to the network and to everyone else. Okay, we'll come back. A node processes all its received TC messages, but only forwards TC messages if the sender is in its MS. What is it now in the English? See, this you can help me with. What is happening here?
Since the code is NPR node or something,
Yes.
it has to forward the TC message for that.
Right. If I receive a TC message and if that sender is in its MS set, that means he elected me, he asked me to be the relay, right? Then I should forward his message. So if I am the elected person for somebody, then I should forward the message.
So basically, my MS is someone else's NPR or MS.
Yes.
So basically, I need to forward that information that I can do to relay.
Yes, yes. And whoever has selected you, right? And this will go on. And we're talking about 3 hops, 4 hops, and n hops, right? Now we are reaching where this will go on and on. So TC message will go to the entire network, but it will only go through some nodes. And it will only talk about some links and not everybody. Okay. Okay, so it's there. So TC message, it lists list of advertised neighbors. So basically the link information. The neighbors. So if you have any questions in this or this, you can ask me. What is happening? So who will generate the TC message? Only MPR nodes. Only relay nodes will generate TC message, rest everybody is quiet. Okay? And who will process it and forward it? right? If and you forward the TC message, if you receive a TC message from somebody, you forward it if the sender is in its MSC. The generator of this message has selected you to forward it, or selected you to be the relay, you will forward it, right? And only NPR node forms, right? So now you can see there are some nodes in the network which are relays which are above, right? One layer above, and they are only talking. Rest everybody is quiet, right? And you generate messages for the labels, right? In the manner which we'll see very soon. Derive it correctly, right? So we have a pair of 1, 4, 3, 4, 3, 6, right? This is. Oh, by the way, we didn't talk about 7. That's easy. So this is just like you derived. Okay. So now let's execute the protocol. So node 3 will generate a TC message, right? Which is an NPR node. So we will generate a TC message advertising nodes in place of 3. So it will say 2, 4, and 5. Like this thing. So 2, 4, and 5 have selected me. From me, right? So it generates a TC message. It will broadcast it. So 2 will receive it, 4 will receive it, 5 will receive it.
Is this TC message similar to the hello message which you sent?
Yes, but the contents are different.
Yeah.
Yes.
So why this? How does the node 7 before that hello thing?
No, hello has happened. Right? All the session of hello, 3 rounds of hello, as I said, and that has is over, and with that you just come up with NPRs and MS. So then first when you switch on and you start saying hello, then after exchange of hello messages, you learn something about your one-hop neighbor, you learn something about your two-hop neighbor. You use that information to find out NPRs, information to get MS. And if that all information is in place, now you generate your first TC. TC message, it says for node 3, it is MS of 3. So who all selected you? So this information is there, but now 3 is saying to somebody, right, that I have been selected by these three, which is not there as it is in heaven. So you are deriving this after the series of hello messages, and this is something new which is not there in the heaven. So you 3 will send it, okay, and everybody gets it. 2 gets it, 3 gets it, 5 gets it, right? And then what happens is node who should forward it. Node 4 forwards node 3's TC message because node 3 belongs to MS of 4. Yes. No, optimality is done. Once you get the NPR set, value is done. See, now we still don't, so our final objective is routing. Our objective was not to say to hello message. And our objective was not to find out NPR, MS or anything, right? The final objective here, what we want to reach is the end-to-end routing. Right? So that is where we are going. All this was just the preparation, right? The raw material. And the real thing will start from now, when you have the entire routing. Right, so that we'll see now how it is evolved. But not the entire network. If you want to have an end-to-end route, I'm just jumping now, right? If you want to have from source to destination, that is the thing. Just by knowing NPR and MS doesn't tell me if I want to send packet from here to US or from 1 to 7, what should I do? No. See, the hello messages is something I never said what is the minimum cost of packet. I didn't say what is my next home neighbor if I want to get minimum dispatch. See, this was just your local neighborhood discovery. So we will come to the link state finally, and we'll then do a comparison. So stay with me. I will write this. It's more important. So what has happened so far is we have MPRs and hello messages and all that, right? And I'm generating a new message. But just remember, finally what we derive is an entire path from a source to destination.
So, in the MS of 3 we have 4.
So you're talking about this.
Right, row 3. We could be forwarding the DC message to 4 and 5. Right? Because
So first let's talk about generation of TC. Let's see, you now understand who generates TC, right? And the relay nodes will generate TC, right? And what is the content of this TC is it's MSC, right? So it says 3 will say that I am being relayed for 2, 4, and 5, right? And that message comes to let's say 4, and we'll see what happens at 4. And let's run through this example and finish it. And node 4 will forward 3 CC message because 3 belongs to S of 4. What does it mean? Four will forward 3 CC message because 3 has designated 4 to do that. Right? So that's why 4's obligation is to forward that message coming from 3. Right? And node 6 will forward PC of 3. So 4 will forward 6 will forward. Right? See, at first level 2, 4, and 5 get PC message of 3. Then when 4 will 2 forward it, that's a separate question, then it will not. But when 4 forwards it, 6 will get it and 1 will get it. Right? So now the question is whether 6 should transmit it. 6 will forward PC3 message because 4 has selected 6 to do the forward. Right? And 6 now gets a copy of it. Right? And so on. And it will keep going as if you get a message from a node who has selected you to be the relay, you will forward. Right? So only those nodes will forward which are the relays who have been selected. And only those generate the message who are relays. Yes. See, 4 will generate it if it's select is an NPR node. Right? So 4 is an NPR node. So 4 will also generate the DC message, which will be what? Yes. So 6 will forward all the messages of 4. No. So this we are not talking about the wireless interface right now. And let's assume that the MAC layer is equal. Right? But see, 6 will forward all messages coming from 4 because 6 is the relay of 4. Which message is not important? Yes, so yes, 6 will forward it and vice versa also.
So, one route I have is once 3 has forwarded to 4, now 4 has to forward to its MS code. The option for that is 1, 3, 5, 6. So 4
So 4 will send it to everybody.
So 4 will send it to only its MS cell, right?
Yes.
So it will send it back to 3 because it has received from 3 students.
Right, so it may or may not, if it does, we will ignore it. But there are other new contents. You see, if the same message bounces back, you will ignore it. Right? But if it's a new piece of information coming, because there could be nodes on the other side of it, right, which you then have to forward. If 3 is MPR of 4. Last one. So 3 generates a PC message, 4 gets a copy of it, 4 will forward it because 4 is relay of 3. And now when 4 forwards it, 6 gets a copy of it. And 6 will forward that message because 6 is the relay of 4. And you now continue with this relationship. 6 will forward this one, whoever is the relay of 6 will forward TC3 message. Right? So TC3 message is now going very far. And we keep going through the chain of the relay nodes. Right? So now let me just finish this as compared to link state. In link state, what used to happen is everybody generates message, everybody gives it to each one of neighbor, and everybody forwards it. In this case, only few nodes generate the message, some topology message, They give it to their one of neighbors, and only the selected node forward it, and so on. More file. Yeah, it will get it. Yes, but the thing is, if find the relay selected by 4. No. Right? No, it gets it. Yeah, so getting it, everybody, I broadcast it, it's like shouting. Everybody goes around me. Right? Our more question is, see, hearing is, let's say, inexpensive, it's free. If I hear something, it's free. What I want to reduce it, whether to say or not. Whether to talk or not is the question. It's not about hearing. If it actually hears it, I don't get. Right? But the question is whether I should speak or not. Let's do it. First of all, we'll mode 1 generate a TC message. Why will 1 generate a TC message? Right? So nobody selected 1. Right? So it's not going to generate a TC message. Right? So nobody in the network will probably know something about 1. Whether 2 will generate a TC message.
If NPR 4 was 1,6 instead of 3,6, it
Yeah.
can be 1,6 as well. NPR 4.
Yeah, then there's a different story. Then one will generate a TC message. In our case of this scenario, right, nobody selected. That's why we are not. If one was selected instead of that, then it would have. Will 2 generate a TC message? Nobody selected 2, so 2 is not going to generate a TC message. Yes. No. That's the beauty of this promotion, right? 1 and 2 don't generate a message. We will see what happens finally. If we don't generate a PC message, there is an implication of that. Right? But in our network, 1 and 2 don't generate anything. 3 will generate, of course, because 3 has been selected by 2, 4, and 5. And we saw this example. 3 generates this message, and we saw how it goes on. Right? Will 4 generate a PC message? 4 will generate a PC message. It contains will be 1, 3, 5, 6. Right? And who will forward 4's message is this below. Whoever has been selected by 4. Or whoever 4 has selected, 3 and 6. 3 and 6 will forward 4's TC message. Will 5 generate a TC message? Right? Nobody selected 5. So 5 is not going to say anything. Will 6 generate a TC message? Right? 6 will generate. We didn't write about 7. But will 7 generate? Right, so just to give you the whole thing, right? So 7, nobody selected 7. Right, so 7 is not. So what did we gain after all this exercise? Did we gain something? What is the gain? Right, we got very few messages generated now in this example. Right? Not everybody is saying the TC message. They say hello messages, but they don't say everything. Right? They don't generate TC messages, and we should save on TC messages because that's the message that goes from one end of the network to another end of the network. Right? So we saved on lots of messages. Right? So OLSR is better than link state routing. Right. So it doesn't fully ensure, but it cuts down. I'm not saying that I have sufficient and necessary part of it. Right? I have the necessary part, but right, I might have something more on that. Yeah.
Like we have now a network of relay agents. Right?
Yes.
What we can do is like create another layer of the super relays for the relays agents.
Okay, we'll come to that. right? But our protocol is not yet finished. Let's finish this one. We don't have time, so right. But let me just give you an idea that these are the TC messages, right? Which is the topology messages that goes across the network, and then every node will get this TC message, and they can find out some routing of it. Right? Do you know how they do it? Do you have all the information in all these collection of TC messages to send data from source to destination? That's the question. Don't think about it from mathematical point of view. Just think about if I collect all these TC messages, how would I get end-to-end routing? Then do I have everything? So what do I need to send a packet end-to-end? I should know every single destination should be there somewhere. If that destination is missing in all the TC messages, I will not be able to talk. Let me ask you a simpler question. If I just have TC messages, just you can maybe go home, write down all the TC messages that you generated, and see using all these TC messages, can you get a route from source to destination? The question is, when you just get all the TC messages like this, TC of 3, TC of 4, TC of 6, and so on. See all the messages. See, can you use this set of TC messages and find out a route from source to destination? You think you can do it? How many of you think you can do it? How many? It doesn't matter. And if you think that it's hard, how many of you think that if I just get the TC messages, I cannot go from source to destination? Because there's just too less information. So TC of 3 is saying 245. TC of 4, so basically these are the TC messages, right? TC of 3 is saying 245. TC of 4 is saying 1356. TC of 6 is saying 4 and 5. So let's see what it's saying. 3 is saying 2, 4. TC of 4 is saying 1356. 1, 3, 5, 6. TC of 6 is saying 4 and 5. TC of 6 is saying 4, 7. So this is what you're saying. I sometimes get more information. So this is what you're saying. But this is what typically I see. Now, is this sufficient for do the routing? Is this sufficient enough, this information, to send the packet from any source to any destination? You need any more information?
6 comes you need to do 7 with the 6 comes
Yeah.
we did not calculate.
We did not think about 7. So what was the 7 part?
Calculate MS.
MS of 6 were 4, 5, and 7. Yeah, I think we didn't in this particular example, right? We didn't put the 7. So that's why 7 is missing. So now is this sufficient? All the TC messages, right? What is the difference between the real network and this network? So 1 to 2 is not connected in my messages. Right? When the real network 1 and 2 are connected, they know each other, right? And if anybody other than 1 and 2 wants to send to 1 or 2, right? In any case, I don't need to send it via 1 or 2. It will come to 1 and it will come to 2, and that's the optimal part. So now think about it, we'll come back to this part. Right? So the thing is, we started with one network, we did lots of journaling, and finally we came up with this network, which is different from our real network. So what I'm saying is, this is sufficient. to do optimal routing. You don't need any other information other than this. I send very less messages. I save down energy and nodes. Only few nodes forwarded it, and I gain out so much out of it, but still I am not losing out the path from source to destination.
This is sufficient because we consider all hops of particular level.
Yes.
But if in DSPM you cannot do all the hops. One to four distance will be more than 4 to 3 distance.
So we will put weights. For now, our weight for every link is 1. We can put that. Right? We can give different weights to every link. That's okay. So that's independent. Right? And with that, we can calculate the actual cost. Right? So we started with link state protocol, right? And we know there are a lot of messages. We came up with a protocol which sends very few messages and which forwards very few messages, and we derived a new network out of it, which is not the real network, but still we did not lose out on anything. We can find a path from any node to any node, and I'm also saying that it will be an optimal path. Right? So that's the better protocol as compared to what you know link state. And we'll go through this example again next time. Okay, so Nikita, come back. Nikita will send you the reasons for rejecting points. Right? Once you get it, then only you talk to the examiners. Why and so. Right? Don't you send emails before that. Okay, and I will post an assignment on all of these, and I will give you a template for your final report of the for the project. Okay, so let's start.